So now let's take another look at the slow leak problem. We are going to show this problem can also be solved using variant of Dijkstra algorithm. So in fact, that illustrates sort of the versatility of the Dijkstra algorithm. So just to refresh your mind, so this is we're trying to see whether we can go from school to home and the shortest distance, but we have to basically stop at this airing station, repair stations, before we go too long. So we start at this with the value d, but then we sort of consume that on the path. So the standard solution is to use Freud washer twice to compute the shortest distance between every pair of repair stations, including the school and home. But we can also try to use Dijkstra. So the idea is we sort of try to find what is the best state when we reach each of the nodes. So in this case, the distance that have traveled is not the total distance we have traveled from the school is not the only parameter. The other parameter is sort of how much air we have. So we are basically sort of comparing two things, the distance we have traveled since leaving school and sort of the distance we have traveled leaving the most recent repair station, so which basically give how much air we are left. So essentially we're trying to find the optimal, we're trying to find things are sort of optimal in both sense, so we may have two states that are incomparable. So for that, we'll simply remember both of those states in the Dijkstra algorithm. So let's see how that works. So for this, I used another class called node, which record the information of which node we are at, how long we have traveled, the distance d, and the remaining air. So, and the comparison is we will compare based on distance. Yes. Okay, so let's look at the code here. So we are going to store sort of a list of best solution we have found for each of the node. So it's not just the shortest distance now. It's rather the best shortest distance together with the maximum air that are left. So we have a priority queue, which will take the node. And so we start by having the distance 0, and we are starting at the node 0, and we have a d amount of air left. And so while the priority queue is not empty, we take it out, and if the node ID is n-1, that means we have arrived home. Because the priority queue is primarily based on the distance traveled, so the first thing we find will be the shortest distance. So we have reached home. And then so now we have this new node that we just extracted from the priority queue with this distance. So the question is, does this give us a better solution? So in the standard Dijkstra, what we do is we simply compare the distance from here with the distance that is stored. So if it's smaller, then we know we find a better solution. So otherwise, we will not process it. But here it's a little bit more difficult to just compare the distance, because there's in addition to distance, there's also how much air that remains. So for this one, we will check whether there already exists a solution that's stored here that is strictly better than the solution we just find, which is the NN. So NN, what we take out from the priority queue is a new solution, which include the distance and the amount of air left. So these best are all the solution we have stored for this node. Sort of what are the best the things that are, I guess it's not sort of bad. It's rather these are the solutions that are not strictly better than any, not overshadowed by any other strictly better solutions. So if this NN is strictly worse than one of the existing solutions, that means the distance is greater than equal to the node system, and its remaining air is less than equal to that, then we don't need that. So we just simply skip the rest of the loop, and then we will extract the next one. Otherwise, then that means we have find a new solution that's sort of better. We just add it, and then we will use this to again go through all the edges, and then see, because now we may be arriving at a node with a little bit extra air. So then this may enable us to reach other repair stations that couldn't be reached by previous route. So we sort of need to go through this thing again. So for all the edges of the node we are talking about, then we will see if we traverse this edge, do we have any air remains? If the edge is greater than equal to 0, then that means we can reach them. So then depending on whether this is a repair station, if it is a repair station, then we will refill air. So then this value will reassign to D, so then we can check only when this is greater than 0. This will be used for node, because if this is 0 and we reached a non-repair station, we're stuck there. So if we reach a repair station, then it's already refreshed to D. So here the condition is if this is greater than 0, then we will add this to priority queue, which says now we find a way to reach this node, and we have traveled this distance, and this is the amount of air that remains. So then these are put into priority queue. Next time when extract, then we will compare that with the things we've stored about this node and see whether it gives us a better solution. So I think for this solution, it is possible to come up with test data so that this will run very slowly, because you may keep discovering sort of slightly better ways of reaching a node with a slightly more air. And then you will keep adding things to the queue. But as it turns out, this algorithm actually, I think this code actually passed the solution. So this is not sort of the ideal solution for this problem, because of this lack of guarantee that it will pass given the parameter size. But this I want to discuss this solution to illustrate the power of the Dijkstra algorithm. You can, especially implemented using a priority queue, because you can do things like this, throwing multiple solutions for a node into the queue and then take it out and process basic. And I've seen quite a few problems that can be solved this way. Okay, so finally some hints for the problems that are in this week's problem set. So for flowery trails, this is essentially the problem asks you to find the edges that are part of some shortest path from the source to destination. So there may be multiple paths that have the same distance. So then you want to sort of keep track of all of those paths. So this is a single source shortest path, but you need to compute more than the distance, but also the edges that are used. So you need to keep information to reconstruct the shortest path, and also in the standard Dijkstra algorithm, if you see a path of equal length, you simply ignore it. You don't do anything. Here you need to keep track of that information, because that's also a equally short path. That those edges also need to be considered for the solution to this problem. So then you can, again, this is something you can use priority queue sort of putting a little bit of extra information into the things that you add to priority queue to keep track of this additional necessary information. For the other problem, so for the Nicola problem, because the movement depends on the length of the previous jump, so you can use both the length and position at the state. So this will result in up to n square states. This should be nodes for states. And because n is 1,000, this can be 1,000,000. But because at every state, you can only jump to either forward or backward. So there's only 2 edges out of each state. So the number of edges is up to just 2 million. So that if you write your implement your code right, it's actually doable using Dijkstra. And this other problem is use Floyd-Warshall, sort of all path shortest all pair shortest path problem. Okay.